Reactions which are reversible, meaning reactants can change into products and then products can change back into reactants, have a double-headed arrow. The reaction can reach something called equilibrium. The definition of equilibrium is that the concentrations are constant, Cc, and that the rates are equal. So let's look at graphs which show concentration. The y-axis will let you know that you're working with concentration and the units are mole per litre. At time 0, you will always have 100% reactants and 0 products. The reactants will decrease over time as they change into products, and products will increase over time as they are made from the reactants. Now remember our definition, concentrations are constant and rates are equal. We would draw a dotted line to show at the point where the concentrations are constant. That means that the shape of the curves do not change. This past paper questions from the Higher 2008, written 10A. The graph shows the concentrations of cyclopropane and propene as equilibrium is established in the reaction. Mark clearly on the graph at the point in which the equilibrium has just been reached. So we need to remember our definition, concentrations are constant and rates are equal. If we look at the y-axis, we can see that we're working with concentration, so we have to look at the point in the graph in which the lines are constant, that there is no change. We'll put a dotted line to show exactly where the position of equilibrium lies. Now let's have a look at graphs which show rates. The y-axis will let you know that you're working with rates and the unit is per second, or s to the minus 1. At time 0, you will always have 100% reactants and 0 products. Remember our definition. Concentrations are constant and rates are equal. So at this point in the graph, because we're working with rate and we're looking at the definition, we want to find the exact point in which the rates are equal. That means that both curves meet at the same point, and this is where equilibrium is achieved. This past paper questions from the Higher 2009 multiple choice 34. Steam and carbon monoxide react to form an equilibrium mixture. Which of the following graphs shows how the rates of the forward and reverse reactions change when carbon monoxide and steam are mixed? Remember our definition, concentrations are constant and rates are equal. On the y-axis we can see that we're focusing on rate, so we want to find a graph in which both of the curves become equal. So the correct answer to this past paper question is multiple choice answer B. So let's look at graphs that show the impact of catalysts. Catalysts do not change the position of equilibrium, but do increase the rate. Now remember, when you're adding a catalyst, you're not changing the number of reactants, so the graph that you add must start and end at the same point. The steeper the curve, the faster the reaction. So when you're drawing your curve, it is going to be lower than the original curve, starting and ending at the same point. This past paper questions from the Higher 2009 multiple choice 34. The graph represents the change in concentration of a reactant against time during a reversible chemical reaction. In which diagram does the dotted line show the result of the repeating of the reaction using a catalyst? Remember, a catalyst speeds up the rate of the reaction. You're not changing the number of reactants, so it must start and end at the same point. And the steeper the curve, the faster the reaction. The only graph which starts and ends at the same point and shows the dotted line which is steeper is multiple choice answer B. The next factor that we're going to investigate is the effect of pressure. Pressure can only affect substances which are in the gas state. Here we've got the same equilibrium, and what we're going to do is we're going to draw a box to represent the reactant particles and a box to represent the product particles. How many moles of reactants in the gas state do we have? We've got 1 for the nitrogen, 2 for the oxygen, so that's a total of 3 moles of gas. On the product side, we have got 2 moles of gas. So if we look at the left-hand side, we can see that we've got more moles of gas, which means we've got less space. On the right hand side, we've got less moles of gas and we've got more space. The story that I use to help me remember how to do this is I think about a headache. When I've got a headache, I've got a lot of pressure. So that's represented pictorially by the reactant one. There's lots of particles squeezed in a smaller space. Do I like a headache? No. What am I wanting to do? I want to decrease the pressure, which means if I decrease the pressure, the equilibrium would move to the left. However, if I wanted to make more product and shift the equilibrium to the right, I would do the opposite and increase the pressure. This past paper question's from the Higher 2006 multiple choice 33. Gases, iodine and hydrogen were reacted together in a sealed container. Which of the following graphs shows the pressure inside the vessel as the reaction proceeds at a constant temperature? First thing we have to do is we have to draw down our boxes and identify how many moles of gas we've got in our reactants, which is 2, and how many moles of gas we've got in our products, which is also 2. Because they've got the same number of moles, pressure would have no effect on the position of the equilibrium. And therefore the correct answer to this past paper question is multiple choice answer D.